So we're looking at section 12.1, writing arithmetic sequences. So we want to be able to write arithmetic and geometric sequences, both recursively and with an explicit formula, use them to model situations and translate between the two forms. So first we're going to do kind of an investigation here. So let's say we've got a staircase where the vertical distance between steps is 7.5 inches, and you must walk up 14 steps to get from the first floor to the second floor, a total vertical distance of 105 inches. So we're going to have two functions, BS, which models the distance from the bottom of the first floor to the top of your foot, and TS, which models the distance from the bottom of your foot to the top of the staircase or the second floor. So for both functions, the independent variable is S, which represents the number of steps you have walked up. So starting with our function BS, so that's our distance from our foot as we go up the stairs. So we're starting on the floor, so our distance is 0. At the first step, we're adding that 7.5 inches. So our distance would be 7.5 inches. On the second step, we've gone up 2 stairs. So our original height was at 0. We're adding 2 stairs of 7.5 inches each to get a total distance of 15 inches. So hopefully you can see where this is going. Our third step would be 0 plus 3 times 7.5, which is 22.5. And then our fourth step would be 0 plus 4 times 7.5 to get us to 30 inches. TS is kind of backwards. We're going down. So it's our distance from the top of the stairs. So we're starting at the top at 105 inches. So we'll have to this time subtract for each step. So 105 minus 7.5, which is 97.5. And then on the second stair, we're subtracting 2 stairs of 7.5 to get us to 90 inches. Continuing on, 3 stairs to get 82.5, and then 4 stairs to get 75 inches. Oops, yeah, scroll now. Oops, sorry about that. So based on the patterns in the table, write the rules for the two functions. So as we started going up the stairs, we started at 0, and then we took 7.5 inches times however many steps we were at. Our function TS, when we were going down, we started at 105 inches, and then we subtract 7.5 for each stair. So the domain, what are all the possible inputs? Well, they have to be whole numbers. You can't go on a partial stair. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 until we get to the 14th step. The range, what are the y values? What are the distances? Well, that's going in intervals of 7.5. So it started at 0, and then we had 7.5, 15, 22.5, 30, 37.5. Again, going in increments of 7.5 inches until we get all the way to 105. So we can graph these points. I'm only going to graph some of them, the nice even ones. So we had 2 and 15, 4 and 30, 6 and 45, 8 and 60, 10 and 75, 12 and 90, and then 14 and 105. Now, again, we will have those other increments in here, so 1 and 7.5. You'd have all of those as well. I just don't feel like graphing them. And we're scrolling. So you can see that here, the domain and range. We've got all of those. We're looking here at TS now. So the domain, the possible inputs, we still have the whole numbers because we're still a whole number of steps. And then the range, this time we're looking at it kind of backwards because we're going from the top to the bottom. So this would be your graph there. So both TS, BS, and TS are linear functions, but the graphs consist of discrete points. Why didn't we draw a line connecting all of the points on our graphs? Our inputs are only whole numbers this time. You can't step on a partial stair. So our inputs are only whole numbers, so we can't include all the in-between points. So we won't be connecting our dots here. So how are BS and TS different? The main difference is that BS is increasing. You're going up the stairs, whereas TS is decreasing, essentially because you're going down the stairs. So a sequence is an ordered list of numbers. Each number in the list is called a term of the sequence. You can think of a sequence as a function with a subset of the integers as a domain and the set of terms of the sequence as the range. An explicit rule for a sequence defines the term in position n as a function of n, and then a recursive rule for a sequence defines the term in position n by relating it to one or more of the previous terms. So the explicit, you write position n as a function. So it's if you're finding an individual position, whereas a recursive is a little different. You're finding the position based on your other positions. So what we're going to use these for, the explicit, is if we want to find specifically what's happening at one position, whereas a recursive, we'd want to see what's happening at all of the positions. An arithmetic sequence, also known as a discrete linear function, is a sequence for which the consecutive terms have a common difference. So for instance, the terms of the sequence 0, 7.5, 15, 22.5, so on and so forth, which are the values of BS, they all have a common difference of 7.5. If you take each term on the right, subtract the one on the left, you'll get 7.5. Likewise, the terms of sequence 105, 97.5, 90, so on and so forth, the values of the function TS, those have a common difference of negative 7.5. So that means both sequences are arithmetic. You can write different explicit and recursive rules for a sequence depending on what integer you use as the position for the initial term of the sequence. So normally we start at either position 0 or at position 1. So this table shows the different rules we can have for the given sequences. And then we'll apply these in more general here down in the paragraph at the bottom. So we've got our sequences. On the left is BS, on the right is TS. So the explicit rule is essentially what we found before, our original function. So f of n is equal to 0, our initial position, plus 7.5 n for n between 0 and 14. Those are the different stair values. Let's say we started at position 1 instead. Our function would be 0 plus 7.5 times n minus 1 for n between 1 and 15. So the recursive rule. Recursive rule, you have to give what's your initial position. So f of 0 is equal to 0. We're starting on the ground floor. Our position is 0. And so then the function is f of n is equal to f of n minus 1 plus 7.5 for n between 1 and 14. So what you're doing is you take your previous answer and then you add 7.5 each time. So you have to find each value in order to find the next position. If it starts at position 1, so we'd say f of 1 is equal to 0, and f of n is equal to f of n minus 1 plus 7.5, this time for n between 2 and 15. So similarly, here with TS, we'll have f of n is equal to 105 minus 7.5n. And then with the recursive, we have f of 0 equals 105, that's our starting position, for f of n equal to f of n minus 1 minus 7.5. So, here's the general rule. This is the important bit here. When 0 is the starting position for the initial term A of an arithmetic sequence with common difference D, the sequence has the explicit rule f of n is equal to A plus D of n. D times n for n is greater than or equal to 0. So your function will be your initial position plus the difference times n. Recursive rule. F of 0 is equal to A, so where you're initially starting is equal to your value A. And f of n is equal to f of n minus 1 plus D. So your new position is equal to the previous value plus D for n is greater than or equal to 1. It changes a little different when 1 is the starting position of the original term. The sequence has the explicit rule f of n is equal to A plus D of n minus 1 for n is greater than or equal to 1. And the recursive rule f of 1 equals A, and f of n is equal to f of n minus 1 plus D for n is greater than or equal to 2. So we'll see how these work here in the next video.